Talk a little bit about first law of thermodynamics, which is a fundamental aspect in mechanical engineering. It allows us to determine the change in energy within systems of control mass. First up, control mass is obviously is a system in which only energy can be exchanged between barriers. No mass can flow between in or out of a control mass. This is an example of a control mass, very popular one. A piston cylinder device with air contained inside of it. If you apply an external pressure onto the piston, it's going to store energy in the form of potential energy within the chamber. And as soon as you let go of the piston, it's going to expel energy and output work. And work we define as the integral of pressure over a differential volume. Typically, the pressure is constant, and you just take the integral of volume. And it's kind of ceremonial to how we define what is negative work and positive work. Here at LSU, we say negative work is work done by the system, and vice versa. This is the energy equation. It's basically the sum of internal energy, kinetic energy, and potential energy, and we'll dive into some of the terms. Internal energy can usually be found within most experimentally derived tables. Given your other parameters such as pressure and temperature, you can find your specific internal energy and multiply that by your mass to determine what the actual internal energy is. If you don't have tables, you can use the equations. The only difference for solids and liquids and ideal gases is that we say Cp is not equal to Cv for ideal gases. We use the Cv term for control mass systems. It's obviously different for control volume systems. And for solids and liquids, we say Cp is equal to Cv, so we just use constancy. Kinetic energy, we all know, is just 1/2 mv squared per volume. Potential energy is just a function of the mass and height of the system. So how does the energy equation relate to thermodynamics and the first law? Well, this equation is a state equation which will define the energy at a certain state of a control mass. And so in order to find the change in energy, we come up with the first law of thermodynamics, which I don't have time to revise, but this is it. And essentially it's total energy of state 2 minus total energy of state 1 is equal to the change in heat minus the change in work. Expand the left side, you see the terms that we went through before here. You have your internal energy, kinetic energy, and potential energy. So an example, a really basic example here, we have the piston cylinder with air in it we saw before. We say that state 1, it's at a certain temperature, pressure. In this case, the piston is massless, so we just say it's at atmospheric pressure. And in state 2, the air is cooled, and which decreases the volume of the air. So step 1 would be just define the control mass as the cylinder. Then we write out the law, expand the left side of the equation. We get all these terms, and you can double click. So because the piston is massless, we can cancel out potential energy terms, because if the piston did have mass, then we could leave that in there due to the change in height of the piston, but we cancel out in this case. There's no change in kinetic energy. So the total energy of the system is related only to the internal energy. You can find the internal energy using tables or equations we had before. Given the specific volume, temperature, so you can find that for air. Now solving the right side of the equation. I never mentioned we're trying to find Q, and that's the whole idea. We can find work by simply using the tables again to find the specific volume at state 1 and state 2. And or it can be given, you know, a lot of times it's given as well. And then we solve for work. Pressure is constant throughout the process, so that can be pulled out in front, and then we can come to a return cube. Final topic is a polytropic process. This is just it's a special case in which the pressure volume relation can be written as PV to the N is constant. Typically, this relation arises in certain gas state change problems. It's seen in practical purpose sometimes, but it's mostly theoretical. Yeah. So that's a relation we came up with to describe certain aspects of certain processes. So that's it. Any questions?